Welcome to the Explainer. Today, we are putting on our detective hats. Well, our thermal detective hats, to be exact. We're stepping right into the classic Class 11 physics practicals to track the invisible flow of heat. We'll be starting with some centuries-old science and, as you'll see, finishing up with some surprisingly modern tech. So, right off the bat, here's the ultimate challenge. How do you measure something you literally can't even see? Well, by setting up very specific controlled lab environments, we can actually track thermal energy. We can measure exactly how fast heat escapes an object and precisely how much thermal energy a material can hold. Here is our roadmap for today. We'll cover 1. The science of heat flow. 2. Newton's law of cooling. 3. Plotting the cooling curve. 4. Specific heat capacity. 5. The method of mixtures. And finally, 6. Modernizing physics lab experiments. Okay, let's dive right into Section 1, the science of heat flow. Fundamentally, heat is the energy that produces the sensation of warmth. Now, we often mix this up at everyday conversation, but while temperature is just the measurement on a scale, heat is the actual thermal energy on the move from one thing to another. And that brings us to specific heat capacity. Basically, this is the amount of heat required to raise the temperature of a unit mass of a substance by exactly 1 degree Celsius. Copper, glass, water, they all hold thermal energy uniquely. It's almost like a thermal fingerprint, and that's exactly the mystery we're going to solve today. Let's shift our focus to Section 2, Newton's law of cooling. The formal basis for convective heat transfer actually started right here in 1701. Isaac Newton, Isaac Newton, published his foundational work on cooling anonymously. This laid the exact groundwork for the experiments that physics students still perform in the lab today. So what did he find? Newton figured out that the rate of cooling is directly proportional to the temperature difference between an object and its environment. Basically, hotter things cool faster. But there's a catch for our lab work. This temperature difference absolutely must not exceed 30 degrees Celsius. Otherwise, radiation and buoyancy start to skew your data. To test this out, we use this double-walled apparatus. Notice the water filled in the space between the two containers? That's absolutely vital. It ensures the surrounding environment stays completely stable. We just drop in a stirrer and use 2 thermometers to track that temperature difference over time. Moving right along to Section 3, plotting the cooling curve. In a standard lab observation, you gently stir the water continuously and record the time against the changing temperature. But most importantly, you have to calculate the excess temperature. That's just the hot water's temperature minus the stable room temperature. When you actually plot that out, time on the x-axis and excess temperature on the y-axis, it reveals a classic exponential decay curve. It's pretty cool to see. When the water is really hot, the heat just drops off a cliff. But as it gets closer and closer to room temperature, that cooling rate really slows down and flattens out. Let's move on and see how this builds in Section 4, specific heat capacity. It really helps to compare these two concepts side by side. Newton's law was all about time and speed, how fast heat moves. Specific heat capacity, on the other hand, ignores time entirely. It measures how much thermal energy a given material can absorb before its temperature even rises. Think of it like this. It's about storage, not speed. Which brings us to Section 5, the method of mixtures. Check out the hardware we use for this. Notice the hypsometer on the left? That's a steam jacket used to heat a solid object really uniformly. And on the right is a calorimeter filled with cold water. The entire goal here is to heat the solid up and then safely plunge it into that cold water. The procedure itself is kind of a rapid-fire physical maneuver. You heat the solid uniformly, you record the cold water's initial temperature, and then, very quickly but gently so you don't lose heat to the air, you transfer the solid. Finally, you just stir it up and record the steady, mixed temperature once it settles. So the crucial point is, this relies entirely on the principle of calorimetry, which states heat lost equals heat gained. In our perfectly insulated calorimeter, the thermal energy given away by the hot solid is exactly equal to the energy absorbed by the cold water and the vessel itself. And this equation right here perfectly demystifies that principle. We just expand heat lost equals heat gained by plugging in the masses and temperatures we recorded in the lab. After that, it's just simple algebra to solve for C, the specific heat capacity of our mystery solid. Finally, let's jump into Section 6, Modernizing Physics Lab Experiments. Now, what's really interesting here is how researchers are bringing Newton's 18th century law into the digital age. This setup uses a low-cost Arduino microcontroller paired with digital temperature sensors. So instead of those frantic manual temperature checks with a stopwatch, these sensors stream the data directly over Wi-Fi to a smartphone app. The evolution is pretty clear when you look at the numbers. Manual methods require constant attention, and let's be honest, they risk a lot of human error. The Arduino setup completely automates the recording, with an astounding error rate of just around 0.5% compared to commercial sensors. Plus, it can measure a much larger temperature range. And because this new tech is so portable, students actually took it to the local market. They literally planned an experiment to measure the cooling rates of famous street coffees, just to observe how different ingredients impacted the thermal decay curve. It's a brilliant real-world application of theories from 1701.
So, from Newton's anonymous publications all the way to smartphones tracking street coffee, heat is constantly flowing around us. It makes you think, if you were a thermal detective in your own morning routine, what would you measure first? Thanks for joining us for this explainer, and keep investigating.